Okay, good morning, everybody. Let's get started. Usual question, household things, anything from your side? You want to bring out questions? Project is going fine, I assume. The practicals are all under control. I think Giuseppe ran an extra practical last week to catch up for the first practical. Seems to be all good. The lecture notes are on Wattle, and I haven't forgotten to remove the excess or something. So, all good. Okay, so next question is, what have we done last week? What was sort of the last topic we looked into? Where can we connect this week? This is where you should frantically page back in your notebook and see what was written in the last couple of pages. Very quiet for Monday morning. So we looked at performance, arithmetic performance, and particularly looked at simple examples like a loop. So looking at this very, very simple loop, this is a slide from last week, is what is the arithmetic performance of such a loop and how can we calculate this and then actually make estimates on performance. And we did a couple of examples where we just assumed that these arithmetic operations have certain time consumption, and also load and store operations have a certain latency until you get the data. So in our example, we assumed load and store latency of 2 cycles from and to the L1 cache, and then the multiplication at latency is 3 cycles. And then we allow for superscalarity, that we have a single load store operation, but 2 floating point and 2 integer operations at the same time. And then this sort of information, you can actually calculate how many cycles should it take to execute a single loop operation from this code. Now, we also looked at how we can tune the performance, and we looked at loop unrolling. And I showed you, I'm not going through this again, but I showed you that you can increase performance by increasing the arithmetic density within a loop to a certain extent, for example, by loop unrolling. In particular, for this very simple loop, you actually get quite a bit of a performance improve, that you get actually 1 result every 3 cycles if you multiple unroll this particular loop. But then I also showed you, told you that ultimately this particular loop is load store dominated. So this means at some point it's not limited by the arithmetic you do, but by how fast you access your memory. And this is particular for this particular example, is there's a poor instruction mix at the start of the loop. Even if you unroll, there will be a load store overhead to do. So this brings us to today's topic, which is memory access. And it is important because, as you just saw, even an infinite fast CPU must load and store data from and to memory. So we need large, but also very fast memory to actually feed our arithmetic processor fast enough. And typically nowadays, this is achieved by cache memory, but also wide parallel memory access. So you have wide buses to feed memory very quickly between different layers of memory, but also to the instruction processor. So when we talk about speed, again, we have to talk about time. What is the access time for memory? Memory access time is simply defined as the amount of time it takes to read or write to the memory location. There's another time to consider, which is the memory cycle time. This is really how quickly you can repeat a memory access to the same location. Now, these two things are very, very different, because you can have a very fast memory access time, but possibly a slow memory cycle time. And both of them have to be considered. So for example, a memory chip might have an access time of 50 nanoseconds, but the cycling time may be 100 nanoseconds. So accessing the same address 2 times in succession might actually take 150 nanoseconds, because you have both of these times to consider. Now, also why memory access is important, and probably even more so important these days, is because it turns out the gap between arithmetic performance and memory latency or memory performance has actually gone up in the past and is still actually growing. So if you look at this graph here, so on the x-axis is the time when certain processor generations were introduced, and these processor generation, the data points here are always the latest process generation at processor generations introduced at these times. And on the y-axis is either the arithmetic performance in megaflops per second or the memory bandwidth for this process generation. And what you see is from 1994 to maybe 2004, 2005, it's a relatively equal battle between arithmetic performance and memory performance. So these two kept in line reasonably well with each other. After 2004, there was a change in the architecture. This is where multi-core processors were introduced, and where you see there is the arithmetic performance still increased exponentially. So because here on the y-axis it's a logarithmic scale, so it's really still an exponential increase of arithmetic performance. However, there was a generation change of memory access, and the memory access per processor unit actually fell behind. It has partly to do with this changeover from single core to multi-core processors, but also overall there is a widening gap between memory access and arithmetic performance. So the other thing to consider is that also not only the access speed has to increase, but also the memory sizes are much, much larger today than they have been 10 years ago or 20 years ago. And if you have larger memory to access, of course, pointers are bigger and it will slow things down. So in terms of memory technology, there are 2 main technologies you should be aware of. There are SRAM, static RAM. So in static RAM, each bit uses at least 3 transistors, 6 transistors for the best static RAM, and they need a constant power supply to keep the transistors charged. In the DRAM, or dynamic RAM, each bit uses a transistor and a capacitor, and over time the charge will leak from the capacitor, and therefore it must be refreshed from time to time. But in terms of, so this is how they are different in construction. In terms of behavior, memory behavior, if you compare the static RAM to the dynamic RAM, the big difference is the access time. So static RAM can be accessed much more or much quicker than the dynamic RAM. And because of this reduced access time, it's typically used or mainly used in caches, whereas the DRAM is used in main memory. Now, why wouldn't one use static RAM for all memory caches and main memory? Well, it's mainly the price, because the production cost per bit for the static RAM is much, much, much higher than for the dynamic RAM. So if you want to have large main memory, it just becomes exceedingly expensive to actually build SRAM. Now, in the very old days, some supercomputers like Cray actually did this. They used static RAM for their main memory. There's one other disadvantage from, besides of cost, is because they have to be constantly powered, it also generates heat, and static RAM has to be cooled if it's a very large memory. So back on the Cray again, it was actually cooled with liquid nitrogen in order to keep the static RAM cool enough. And it was a fortune to pay for a couple of megabytes of static RAM. Now for memory access, it involves 3 stages. So memory is laid out in a 2-dimensional way. So you select a row of the address, and then you select the column of the address, and then you do the read or write access to the selected bits of the address. So this is how you access the memory. And then there's, of course, on top of this, that the memory, so you transfer the addresses and the data over the relevant buses from the memory to the CPU, to the arithmetic unit. Just as a sideline, we're not getting into this, but of course, there's also scope for pipelining when you do memory access in a repeated fashion, because you have these 3 different stages, you can actually pipeline memory access. So in terms of memory hierarchy, we already heard there is faster access to caches, but it's more expensive. Modern processors have a memory hierarchy which try to make a compromise between speedy access, but also the cost it produces to produce the CPU. So the memory is organized in hierarchies. So you have registers, which only need a few clock cycles to access. Then there's cache, again, few clock cycles to access. And then you have memory, dynamic memory, and virtual memory, which takes much, much longer to access this memory. And the idea behind this hierarchical organization is that generally you don't need all the data at the same time, and the currently most needed data is brought into the faster memory, and then it can be used by the arithmetic unit relatively instantaneously. So to do this, you make a little bit of a assumption or betting what data is really be accessed next, most likely. And there is the observation that typically memory access in most programs, they have either temporal locality or spatial locality, which means either they have been accessed. So if you have accessed a memory address X, likely you will access the memory address X very soon again. So this is time-wise, there's temporal locality. Or there's spatial locality, which means if you have accessed a certain address X, it is also likely that the neighboring address, the X plus 1, will be addressed very soon. So this temporal and spatial locality of memory, you want to take advantage of this in how you load the hierarchy of your memory. So how do you do this? Caches are not like registers, single words or single blocks of memory, but they're organized in lines and units of L words. And these lines are, for hardware reasons, computer reasons, of course, digital numbers, so binary numbers, which means this L is 2, 4, 8, 16, and so on, exponents of 2. So what this means when you have these lines of words which are in a cache, it means that you don't access or load your cache with a single word, but you load it with a complete line of words. So this is really a blocked memory access. You always load whole blocks of words into your cache. Now, the advantage of this, of course, it's faster and less control needed per word when you do this as a whole line access. And hopefully, if our betting scheme is correct, that there's spatial locality, that the next word is accessed very, very soon anyway, that it's already in the cache and you don't have to reload it. The disadvantage of this is there's redundant memory traffic if you ever only use one word per line. So for example, if you do a pointer list, and this pointer list is just hopping through the memories, and then you do pointer chasing where you go through the list chasing the pointer, this means you will access random locations in your memory which are not spatially related, and therefore you get a lot of memory traffic because you will not only load in the single word which you need, but a whole block of words. So what are typical memory access times from a today or a reasonably up-to-date CPU? So if you look at the Intel Core 7, this spec, registers take 1 cycle to access, so to read access, which is roughly 0.3 nanoseconds. So you take 1 over 2.8 gigahertz, which is roughly 0.3 nanoseconds. L1 cache hit, so if data is in your L1 cache, you will need 4 cycles to access it. L2 cache is 10 cycle access, L3 cache already 40 cycles. And then if you go to your normal memory, your dynamic memory, 160 cycles, and then remote DRAM, which is not the memory which is directly associated to your core, your particular core, but a different core, this can be even higher. So what you see here is you can optimize a lot within your arithmetic operations if you do mistakes of where your data is coming from, that for some reason you make a big mistake and suddenly something comes from your local DRAM, the arithmetic performance will drop, of course, drastically because it takes a long latency, or the latency is very long to actually get the memory in from your local memory. Now, these memory access times include the cost of getting the data over the bus, so you don't have, or in this case, you don't have to worry about the bus speed. The buses are broad enough that within this number of clock cycles, you get the data in. Okay, so this is your memory hierarchy within a normal CPU. Of course, you can also extend this to larger arrangement of memory. On top here, you see the same L1, L2, 3 caches, main memory. But on high-performance computing systems, often CPUs are connected by networks. So you have a HPC network or a gigabit network. They come directly from solid-state disks or local hard disk, and so, or if you do very, very, very large data operations, they might come even from slow internet from across the continent. And of course, the further out you go in this memory hierarchy, the higher the latency, the longer you have to wait until you get data in, and typically the lower the bandwidth is. So keep this in mind. Memory can be very, very large, but the access speed is different depending on where the data is located. So let's look at a little bit of a code. So here on the left hand, you see Fortran code and then the C translation of this. I don't know how much Fortran you have done in your degree, but as you see, the syntax is very similar. You have your for loop here over n, over links n, over variable I, and the same for the second loop here. And then you just multiply these two numbers, I and j, into an array I of j. And on the left side is the Fortran equivalent. The syntax is a little bit different in the Fortran, but I think you understand what the same code is doing. Small difference in Fortran, the C indexing starts at 0, Fortran indexing starts at 1. That's why the loop is actually running here from 1 to n, including, whereas in C it's running from 0 to n, excluding. So what is the difference in this code? As you see, they look exactly the same. However, if you run both of these codes on the same processor and you profile, what you will see is the right code will run faster, much faster, the C code, than the Fortran code. And this is not something to do with that C compilers are much better than Fortran compilers, or C is a better language than Fortran. This is more intrinsically of what you have to know about different languages. Does anybody know why the C code would run much faster than the Fortran code?
Is it to do with row major and column major matrix indexing?
Sir, I can't hear you.
Can you hear me? Yes, I see.
Yeah, now I can.
Okay. Let me give this answer again. So how can the memory cycle time be larger than memory access time? So when you have a memory element, for example, a DRAM, we might have, for example, a capacitor and a transistor. So when you read out the memory element, it will partially discharge the capacitor. So therefore, you have to, the memory cycle time needs to recharge this capacitor, and this takes a certain amount of time to actually do the recharge. So this might be, for example, this 100 nanoseconds, which is necessary after you've done a read to recover what was, or to recharge whatever the information was. However, the access time could be much faster, because once the capacitor is charged, you can access this very quickly, take it out, but then it takes a certain amount to actually recover. Yeah, does this explain why a memory cycle time is different from the access time?
Yeah.
Excellent. Yep, I think This was everything from the chat. So back to this code, why is this Fortran code different from the C code? This is how in these different languages the memory access is actually defined. So let's go back to the C code first. So in the C notation, what you see is the array access is in such a way that the second index is the inner loop. This will be continuously accessed, and the first index is the outer loop, which will be indexed in chunks. So if we if we roll this out in our access pattern in the memory, what this looks like in the C code, we have a strided access of a 1D array, and this reduces the spatial and temporal proximity. So we access the element 0, 0, and then 0, 1, 0, 2, 0, 3, and so on. And then once we are at the end at n, then we have to have this hop, which goes to 1, 0, 1, 1, and so on. But overall, the memory will be accessed in a more or less continuous linear fashion, so linear spatial fashion, accessing next elements. And what we heard before is that in cache, these elements will be loaded already in blocks, we will show again. And therefore, this particular strided access is particularly favorable for the C code. Now in Fortran, it's actually different. In Fortran, the notation is that the first index is the first index is the direct element which gets accessed. So what you do in terms of access here is, if the code as it was written out here, where the second index gets updated continuously, and then the second index gets updated continuously, and the first index on the jumps, you will have access pattern of the memory element, this one to this one to this one to this one. However, these elements are not contiguous in the memory, and therefore have much slower access time than you would reorder them in the other way. So what this means is Fortran just uses a column major order matrix storage scheme, which goes in this direction. This is beneficial for Fortran, whereas C has a row major order matrix storage scheme, and therefore is accessed much quicker in this particular C example. So be aware of this, that there are language differences, and you have to understand what language has which memory access pattern, and then write your code accordingly. So for example, to optimize this code in Fortran, you would swap these two loops out. So making the I the inner loop and the J the outer loop, and then it would have the exactly same or similar or exactly the same performance as the C code. Now, what is the effect of the cache size, how big the cache is on the performance of code, for example? So let's have a look at this very, very simple reduce loop here, where we have a variable s, which we sum up to just the square of some array. So let's say this is, we want to compute the kinetic energy, and the a is the velocity. We have velocity square times a mass, and this is what we sum up as the kinetic energy. Just a reduced loop. What would the effect of the cache size be? So what will happen? The memory elements will be loaded in as cache lines. So having long cache lines probably will help, but also it will slow applications with random memory access. So how does this work with the cache line in an example like this? So at the first time we access here this loop, we have the load operation, And when we do the load operation of this A of I, what will happen is we have a so-called cache miss. The particular daughter is not in our cache, and therefore this is called a cache miss. It's not present, and we have to go into a higher memory hierarchy, for example, the L2 cache, to look for the daughter. Or we look in the L1 cache if it's so it's not in the register, so therefore we have to look in the L1 cache to see this, or if it's not in L1 cache, we have the L2 cache and so on. So here we have the load operation. It's not there, it's not in the cache, and therefore we have a cache miss, and it takes a long latency before it comes from the higher memory hierarchy into our cache. And then we can use the first daughter element after it has been arrived in the cache. Now on the second iteration of the loop, we do the load of the second element. Now, because caches are moved, so filled in by whole lines, not by single elements, it means the next element is already in the cache, and we don't have a cache miss. We can directly use the daughter. And this is going on as long as the cache line is. And then once the cache line is, so once the next element after the cache line is accessed, we get another cache miss, and then the same repeats over again. So what you see here is, if you have a very long cache line, this will help because you only do one cache miss, and then you have many repetition of direct access of the already data which sits in your cache line, which is very good in this kind of example. However, if you have an application with random memory access where the cache line has to be swapped in and swapped out continuously, long data transfers, of course, are not very beneficial. So there's a trade-off of how often you use consecutive data and how often you use random elements. Now, what also helps is so-called prefetching, which supplies the cache with data ahead of the actual requirement. So if cache is used, there's also some betting schemes that the previous cache line will be necessary be accessed very soon, and therefore is already prefetched. So these are extra on top optimization or hardware features which can also help to reduce the latency of a cache mesh. So how is cache actually organized, and how does caches actually work on a CPU? So as we already say, they are organized in lines of cache blocks. For example, on an old Pentium, it was a 8 kilobyte L1 cache, and the 8 kilobytes were organized at 128 blocks of 64 bytes. So it's really like you have 64 bytes and then 128 of these blocks, and each of these 64 bytes is one of these cache lines. Now, if you have this organization of your L1 cache, there also has to be some policy how this memory is managed and how do you replace the memory. For read access, typically the most popular kind of policy is the least recently used cache line will be replaced by a new one. So this essentially means that your temporal dependency, the ones which hasn't been used for the longest, gets replaced. For write access, the situation is slightly more complicated because write access means you have to also synchronize afterwards what was in your cache with your main memory, and so through all memory hierarchies. So there's slightly more complicated policies there. The easiest is so-called write through, which means immediately after you change your cache, you write this through to main memory. And even if it might take longer to write to the main memory, it will be written eventually to the, so it just will initiate it to write to the main memory. Write back is the situation where you not write immediately back to the main memory, but you mark in cache which elements have been modified, and you only write back to the main memory the whole cache line once the data is evicted from the cache line. So, for example, if you have here a cache line with 64 bytes, for some reason the first 4 bytes might have been modified back by writing. Once this cache line is now replaced by some other data, then these 4 first bytes will be written back into main memory. Now, with the replacement policy in cache memory, there is also a policy how you map actually the cache memory to the main memory. And one such policy is just, and this is called associative memory, how you associate your cache to the memory. And one policy might be direct mapping, where the main memory is directly mapped to memory in the cache. So you have really index 1 to 4, or 0 to 3 is directly mapped here to the cache 0 to 3. And once this is evicted out, then the next main memory element gets cached in your cache memory. Now, this potentially has, so this direct associative mapping has potential downside. And here is an example where you can really simplify or exemplify this downfall quite drastically. It's called cache trashing. So if you have a loop which goes here in strides of the cache size in bytes divided by 8, and we do a double precision floating point operation here. So here's an addition and multiplication, and we sum this into the vector A here. But we could do this in strides of whatever the cache size in bytes divided by 8 is. What will happen is that you will have repeated access of the same element in cache. So, for example, 0 to 3 is your cache size. And what we do is in strides of 4 here, we access 0 and 4 and 8 and so element, which means with this direct mapping, we will always access whatever sits in cache at the index position 0. So because we are always accessing in this operation here the same element from the cache, this will become incredibly slow because you get hit with 2 latencies. One is you have a repeated cache miss. The cache has to be always fully loaded in new, but you also get hit in addition with this memory cycle time, which, as we saw just before, can be, or typically is much, much larger than the memory access time. So in terms of performance, if you do a loop like this, the performance will be very, very poor. If you do the same loop with the cache size in bytes divided by 8 minus 1, so you make the stride 1 less, the performance is much, much higher because it doesn't hit the same memory address over and over again. So to avoid this, there is n-way associative association of the memory, which means the main memory can be mapped to alternative positions in the memory. For example, here, the main memory element of 0 can be either mapped to the first index, so the first index 0 in way 0 over way 1. It's 2 different cache elements, and therefore you can avoid, to some extent, this cache thrashing. Now, how does impact of the cache lines impact on the, so how does the cache lines impact on performance? besides of the extreme case of the cache thrashing, of course, the cache size will impact on performance. So if you have a simple loop like this, you have an array of I and you multiply into this array some constant, and the loop is here by a certain stride of k, you can look at what is the performance of this loop depending on this k. Now, the update, the performance what is shown here is not the performance of the total loop here, because this would be unfair comparison, because of course if the stray, so if the k is high, then you go through less elements here in the loop and it should run faster. What's really shown here is the performance of executing a single iteration of the loop. But if you do this, what you see is the performance is relatively high as long as the stride is within your cache line. So if all your data is cached in the L1 cache, you get high performance and you get time. However, if you then if your k gets larger, your performance should go down. Now, briefly, how are these caches in nowadays processors organized, and what do you really have to expect when you do your programming? If you look at the Intel Haswell processors, so this is processors which is release date roughly 7 years ago, something like this. What you see is the L1 cache is divided in two L1 caches. There is instruction in the data L1 cache, organized very similar. So if you look at the data cache, 32 kilobytes. They are 8-way associative. They are organized in 64 sets of 64-byte line sizes. And these caches are shared by 2 threads or 1 core. And then they have access times of 4 cycles for the fastest load to use. So it's a simple pointer access. And the bandwidth is 64 bytes per cycle load or 32 bytes per cycle store bandwidth. And the write back policy is it writes directly back. Now this was 7 years or so ago. If you look at the process which was released half a year ago, latest Intel, the Comet Lake generation, what you see, if I switch around very, very quickly, there was essentially no change in the policies of how it's organized and how the policies have changed. It's the same. Of course, there's hardware change. It's higher clock speeds and other things. But overall, you see there was relatively, well, there's no change, very little change. So it seems that L1 cache of 32 kilobytes is still a sort of an optimal compromise between achieving high enough performance with a minimal amount of cost. The associative rules haven't changed. It's still 8-way. How the cache lines are organized hasn't changed. It's still 64 sets of 64 bytes. And even the bandwidth per clock cycles haven't changed for the read or the write cycle. So you see the requirement from the programs on the processors haven't changed as much, and therefore also the architecture really hasn't changed over a fairly long time in terms of computer architecture. Okay, so just to get you prepared for tomorrow, let's start with a real case example, memory optimization, by looking at an example which is using the Jacobi algorithm. And what we will look at is solving the diffusion equations or physical equation, which is, so if a function, the time derivative of the function is equals to the Laplace operator acting on this function. The Laplace operator is just the second derivative in the second partial derivative in all dimensions. So how do you solve an equation like this? Of course, you can solve this numerically by iteration. And what you do is you discretize this function over space, like over xy dimension. And then you solve the change of this function over time, over a small time increment, by computing the second derivative of the function, so the right side, for the sum over the second derivative of the x and the y dimension. So here the second derivative is again numerically calculated by taking the difference between xi plus 1, y1, and the function of xi minus 1, y1, minus 2 times what the function value at the center is. And then divided by this small increment of what you change the x dimension. And you do the same thing for the y dimension. So in this case, what you solve here is like diffusion. Imagine there's something like a melting of a, so you have an ice block, and how does the ice block melt? The ice block will melt according to the gradient of the temperature around. So this is the second derivative here, and this is how the function will change over time. So how does this look computationally? So this is the stencil update. So if you have a point here in the middle, and you want to update this point by this numerical scheme, what you do is you have to consider all the neighboring points in x minus 1, x plus 1, y minus 1, and y plus 1 dimension to calculate the second derivative. And once you've calculated the second derivatives of them and sum those two together, then the change of the point in the middle will be determined by these second derivatives of the neighbor point. So an update scheme could be simply you go through all the points, and then all the points will be updated to new points by the information of all the neighboring points. So here is a straightforward implementation of this Jacobi algorithm in Fortran. So it's double precision, and so the phi is an array which is a dimension from 0 to I max plus 1 and 0 from k max plus 1. These are the dimensions. And the phi is not only in this x and y dimension, but there is two of these arrays kept at the same time. This is this extra dimension here, 0 and 1. So we have essentially two arrays kept at the same time. One is the original one, and then the other one is the updated one. Then we have some integer variables, t0, t1, which we will use as counters. And then we have a loop of how many iterations we perform, how often we, how many time steps, iterations we do. And then is double loop k and I, which goes through all our x and y positions on our phi function. And once in the inner loop, the update looks like we have the position ik gets updated by I plus 1 k, I minus 1 k, and I k plus 1, I k I minus 1. And what you see here is the t1 and t0 is just the index which we swap around in order to make the difference between what is the updated plane and what is the original plane. And then to do the swap between what was updated and what was the original one, we can swap here this T1 and T1 and T server in just a swap of the numbers. So this is a very straightforward implementation of these updates. What you should do is estimate, look a little bit at the performance of this loop, what is required. There's already a little bit of comment in this inner loop here. We say we have four floating point operations, 1 store and 4 load operation in this loop. So the 4 load operations come because we have to load in these 4 double position variables of the phi function. We have 1 store because afterwards we have to write back the result. And then 4 floating point operations because we have 1, 2, 3 additions and 1 multiplication to do the floating point arithmetic. So look at this code, look what is the possible performance, and then also are there any ways how we can improve the performance based on what we already know from arithmetic performance, but also memory access and how we optimize memory access. Yeah, so that's what we will do tomorrow. Are there any questions to today's lecture? No. I open the chat if somebody. There's still an old chat from Callum asking, has anybody else lost audio? I hope the audio is all back. Cat is smiling, so I assume she heard me. Well, if there's no further questions for today's lecture, then let's end it here. And I see you all tomorrow fresh at 10 o'clock. Okay, see you tomorrow.